All right, so let's go ahead and draw this free body diagram. And I'm going to draw my diagram on the right. Okay, so that's a break. That's 2 kilograms. We have a force going into the wall, so that's applied force. And of course, there's a force going on in the opposite direction. That's a normal. And it has the weight, force due to gravity. So that's mg. And what's the force going back up? What do we call that force? Friction. Okay, and that is the static friction. All right, so these are the four forces. Okay, and I think we can at least find out this one. That's the weight. And we say, well, now if it's not moving, so that means the force in the net force in the y direction has got to be 0. Okay, and again, it is not moving, so the forces in the x direction must add up to 0. So that means we can go ahead and say, well, the static friction, I don't know how much it is, but it's going to be equal to m times g for sure. Because that's the only way that they can all be balanced. And this will be 2 kilograms times 9.8 meters per second square. And that tells you it is 19.6 newtons for the static friction. And then do we have the mu? Yes, we have the mu. So we have the friction, we have the mu. That means we have the normal force as well. So I think we can step aside on the left and find out the normal force. And 0.6 is the mu. So that will be 33 newtons would be the normal force. And that would be our applied force. Okay. So pretty straightforward scenario. If you know one, you know the other. If you see, I think one major struggle that I experienced when I was taking physics is to underestimate the importance of not having a motion, or the importance of recognizing that it has a constant speed. Whenever it has a constant speed, or whenever it's not moving, that means the net force must be 0, and that makes a lot of the calculations a whole lot easier. And if it does not say it's 0 or constant velocity, then you cannot assume so until you find clues or find any explicit statements to say that they are really not moving or it's a constant velocity. So that's the applied force. Is this more than or less than the weight of the brick? Well, the weight of the brick, it's 19.6. So that means the applied force, it's greater than the m times g. And chances are it's very likely to be greater than m times g. Now, if you look at this little calculation right here, I personally haven't seen any mu that's bigger than 1. I know that if it's rubber on concrete, that it's 1, so that's very it has a very strong friction. So if there's anything less than 1 for the coefficient of friction, that means the applied force would have to be greater than the weight of the object. So something that you can keep that in mind. All right.